Okay. Now, elasticity, simple definition. Okay, we don't want to go through the, don't need to memorize all the boring definitions. Okay, now if you look at elasticity, right? What does that really mean? Elasticity, you can say like a property of an object. Okay, a property like a characteristics of an object, just like a characteristics of a person, right? Some person are have different traits, okay, different appearance, something like that. Okay, so elasticity is the characteristics, or you call it the property of an object. Okay, now to define elasticity, it is actually the ability of an object to return to its original shape. Okay, if I write down here, ability of an object, now look at the word here, ability. It is the ability of an object to return to its original shape. So there are, for example, some elastic material like rubber band and spring or string, right? So this material, when you stretch it, when you apply a force to stretch it, okay, it tends to returns to its original position after you let it go, right? Okay, so it has this restoring force. Okay, it restore back to its original position. So this is its own ability to come back to its original length or shape. Okay, so it can be shape or it can be size. All right, so these are examples of elasticity. Now, all objects have certain level of elasticity. Okay, it depends on object that has high elasticity or object that has low elasticity. So for example, rubber band and spring, they both have high elasticity. All right, so later we'll go into deeper what is the reason behind it. Okay, now when an object changes its shape or size due to a force acting on it, the object is said to be deformed. Okay, so I write down here. So when object changes its shape or it is said to be deformation. Okay, so deformation is when the size and the shape changes because you exert an external force on it. Okay, now deformation, there are two types of deformation. First is we call inelastic. Okay, right now, inelastic deformation, and second type is elastic deformation. Okay, now let's talk about elastic first. Elastic, just like the word suggests, right? Elastic is if an object returns to its original shape after the force has been removed, then we call it elastic. Okay, so example, just now the example I've given you, for example, the spring, you pull it and then you release the force, it snaps back, it returns to its original length, right? Elastic deformation here is just direct opposite, right? If an object does not return to its original shape, okay, after the force has been removed, we call it inelastic deformation, okay? Or sometimes you will see the word plastic deformation. Give exercise only. Okay, teacher give exercise only. All right. Okay, now deformation in elastic, we also can call it plastic deformation. Okay, now simply when object does not returns to its original shape. For example, let's give an example here, plasticine. Okay, plasticine is the best example, right? Plasticine, when you press it, it changes the shape, right? Bend downward here. Okay, and when you let go of the force, okay, it will keep on this shape. Okay, so this changes in shape, we call it permanent changes. Okay, permanent changes, it change permanently until you give it another external force to change the shape again. Okay, so this example is in elastic deformation. Now, first, now you know what is elasticity and you know what is plastic and elastic deformation, right? Now let's look at the real topic here, the Hooke's law. Okay, so today we are going to learn about the Hooke's law. So the Hooke's law has something to do with the elasticity, okay, and spring and strings. Here is the chapter where you will see many springs, right? We are working on springs, elasticity. Now, to understand Hooke's law, let me give you an example here. Okay, Hooke's law. Let's say I have a spring attached to the ceiling. Okay, say like this. I draw it here. This is your spring. Okay, and initially the spring, I don't attach any load on it. Okay, it's just original spring. So this is the original length. Okay, L is the original length, and this is the first case is without load. Okay, no load. I write down here, no load. Now, if I attach, let's say I attach a load here, so it will extend, right? It will extend. So this is the equilibrium position. You see the dotted line is the original length of the spring. When I attach a load on it, let's say this is 10 Newton, immediately you will see there is an extension here. We label it as X, okay? X is maybe in cm lah, more realistic, right? Usually we deal with cm because spring is very small, right? Even though the SI unit for length is meter, right? But in this case, in this Hooke's law, you will often see centimeters, right? So it is no problem. You can use centimeter for the unit. Now, back to this one. Now, when you attach a load, it extends at a certain length, right? At a certain length. Now, if you keep on increasing the load, of course, common sense, extension will keep on increasing, right? 20N, then you have this bigger extension here. Okay, if you keep on increasing, and the extension will also increase and increase and increase. Okay, now after that, when you let go, now you remove all the loads. Okay, you remove all the loads, and the spring eventually it will return to its back to its original length L. All right, so no extension here. This is when all the loads has been removed. Now understand, in this example here, we call it, the spring is in its elastic region. Okay, I write down here, all this process, we call it the spring is working inside its elastic region. As long as the spring is able to return its original length, then it is elastic region. Okay, it maintains its elasticity. Now, from here, if I were to plot a graph, okay, so I plot a graph of force and extension. Let's say the y-axis, I put force. So the unit is N. The x-axis is the extension, so unit is cm. All right. Now, if I were to plot this graph, what happened here is you will notice that you will get a straight line. Okay, straight line, meaning that when you increase the force, the extension increase. So in other words, in mathematics, we say that the force is directly proportional to the extension. Okay, so as F increases, the X increases. So force is directly proportional to the extension. So I write down here, this is the symbol means directly proportional. Okay, this one directly proportional. Now in mathematics, right, whenever you have something that is directly proportional to the other thing, what does it mean? Meaning that you can change this one, F, you write an equal sign, and then you put a constant here, kx. Let's just assume k is any number. We call it a constant. Okay, so directly proportional, you can change into this equation here. Okay, so you change the symbol with equal sign, and then you add a constant. Okay, this is for mathematics, right? Now, if you change to here, f equals to kx, and that is when we can get this graph over here. All right? So k is, what exactly is k? If you see here, f equals to kx, right? So you see at the bottom right, I write down bottom right. So your straight line equation is y equals to mx plus c, right? Y equals mx plus c. So if you compare this equation, f equals to kx, since your y-axis is the f, so you write down here, f equals to kx. So here you will see that your y is f, your x-axis is x, okay? And then your intercept, y-intercept, which is the c, is 0, right? Because nothing here, 0. So which is why you see my graph, it starts from the 0 here, right? It starts from the 0 here, the green line. And then the m is gradient. So the gradient is equals to this constant here, k. So if I plot here, this gradient, a small right angle triangle here, right? So you have y, x, m equals to y over x, and that is my k. Now, what is this k here? This constant. Okay, now I will talk a little bit about this constant. This is called as the spring constant. Okay, now let me erase this first because I don't have enough space. Okay, if you want to screenshot here, you can just take a screenshot here before I erase this one. Just take a quick screenshot. Okay, now back to the equation. So f equals to kx, right? So this one is actually, we call it the spring constant. It is a value, a number, and it is fixed for each spring. All right, different springs has different spring constant. Now, let me give you a perspective of what is spring constant. Now, if you take a look at the definition, k, I move this x over there. We use mathematical equation to understand it. Okay, so if this one x, you move it over here, you will get f over x equals to k, right? So k equals to f divided by x. So the unit for f is Newton, and for x extension is usually we use cm. You can use m also, nothing wrong with that. Okay, so n cm. Check my audio. Okay, everything going. Now from here, you can write that the unit is n over cm. Now what does this tell you? What does this tell you? Meaning that the spring constant, it is the amount of force, right down here, amount of force needed to extend or compress the spring by 1 cm. Okay, I repeat, spring constant, you can think of it like the amount of force needed to, you either extend or you compress the spring by just 1 cm. Okay, now to give you more perspective on this one, let me draw these two springs here. Now here you have two different springs. Okay, the first one, which has a smaller diameter, and the second one is bigger diameter. Same length, okay, same length. So original length is L, and this is also L. Now, let's take the first one. This first spring is just a normal spring. Now the second one is let's imagine it is the spring of the car absorber. If you ever seen the car absorber, right, the one that inside, if you look at inside the car, in the wheels there, around the wheels, that region, right, you'll see a very thick spring. Okay, it's very strong. Even you sit on it, it won't bend. Okay, so this spring is very stiff. It's very hard, right? Which is why it is used as the car absorber to absorb the shock, right? So this one, if you compare these two springs, and let's say I apply a force to pull it by 1 cm. Now the first spring here, let's label it as spring A, and the second is spring B. if I pull spring A, certain force, by 1 cm, let's say it takes maybe 50 Newton only, okay, just by 1 cm. Now, if I pull the absorber spring, right, the car absorber spring by 1 cm, what is the force needed here? Is it bigger or smaller than the spring A? Of course, it is bigger, right? Because it's stiffer, it's harder, right? So maybe I need maybe 500 newtons. All right. Now notice that for both springs, I extend it by 1 cm, but the second one I require a larger force, right? A larger force, meaning that the second one, spring B, has a higher spring constant. Okay, higher spring constant. In other words, we can say that it requires higher amount of force to extend the spring by 1 cm compared to spring A. Okay, so another perspective for spring constant is, let me give you another example. For example, if you, okay, you can think of spring constant like the stiffness, right? It is the same. Okay, stiffness, I write down here, spring constant equals to the stiffness of the spring. So what is really stiffness means? You have toughness, you have stiffness, all these things, right? So stiffness means that the ability to resist change. Okay, you can write down here, put an arrow here, ability to resist change. What does it mean? What does it mean, the ability to resist change? For example, let's say I ask you to stand still on the ground here, standing straight up and stand still. Now, I give you a challenge here. Let's say, let's play a game here. If I push you from the side, okay, so let's say I push you from the side, if you move a distance from your original position, or you fall, okay, as long as you move a distance from your original position, then you lose. So your job is to maintain your position regardless of any forces acting on you. Okay, you just want to maintain your position. Okay, and then that's how you win the game, for example. Okay, just say for example. Now, okay, so what happened here is you hold your position, right? You hold your position, and then you lower back, you lower your body, you make your stand firm, right? So now you're ready, right? Now, when I push the force, let's say I push you from the side, okay, you are trying to resist my force, right? You are trying to resist, you're trying to maintain your position without letting yourself fall off. Okay, so meaning that you are resisting the incoming force, you're resisting the external force. Okay, now you might fall, you might lose the game, you might fall, or you might win the game. You might still be standing still there, right? But this one, regardless of the result, you are trying to resist the change. Okay, so you can think of stiffness like this. Okay, you can think of it as the resistance to any changes to the external force. So it's the same concept for a spring. As you try to pull the as you try to pull the spring apart, the spring, because of its own stiffness, it will try to pull your arms inwards. Okay, you pull it outward, it will try to pull back you inwards. This is we call the restoring forces. Okay, the force inside the molecules, it tries to restore back. Okay, so this is the stiffness. Okay, now think of spring constant like stiffness. Okay, now next, spring constant, for example, how do I find it? From the graph, you have F versus X, right? So let's say I draw it out here. This is your F, Newton, and X, cm. So let's say I give you two springs, one spring, one line. Okay, spring, blue spring, and then the red spring here. If I ask you which spring, blue or red, has higher spring constant, how do you find it? How do you tell? Okay, so 0 here, So first you understand that spring constant is the gradient. Is gradient, right? Gradient. So first you have to make sure your graph is correct lah. Okay, your y-axis is force, your x-axis is x. Sometimes they terbalik this one. Sometimes your y-axis is x and then your x-axis is force. Okay, then you have to change. Right? So spring constant is gradient, is the gradient of the curve, right? So which one has higher gradient? The blue one or the red one? Gradient is same as steepness. 斜度有几斜 okay? Steepness. The steeper it is, the higher the gradient. Okay? So if you look at the graph, of course, obvious, you can tell straight away. The blue one is steeper. Okay? The blue one is steeper. So the blue one, the blue spring, will have a higher spring constant. Okay? In fact, if you want to prove it, how do you prove it? Let's say I draw a dotted line here, straight line. Okay, connect to the x-axis. Let's say this is x equals to 10 cm. Okay, meaning that to extend this two spring at 10 cm, what is the force needed? Then you plot the graph. From the red line, you join to the y-axis. Here, this is, let's say, F1, and here you join to the y-axis. Here is F2, right? So to extend both of these springs to 10 cm, the force required is F1 for red one. The force required is F2 for the blue spring. Which force is higher? Of course, the F2 is higher because it is higher up in the scale, right? F2 is higher, so straight away you can see that. Okay, to extend spring, blue spring, I need a higher force. Okay, to extend red spring, I need a lower force. So straight away you can tell the blue one has a higher spring constant. Okay, there are two ways you can tell it. First, you look at the gradient, or second, you plot the vertical and horizontal line, and then you connect, you see the value, which one. Okay, so same here, regardless of how many strings you have, the same graph, you have like this, like this, like this, like this, like this, like this. Which spring has the highest spring constant? Or I can ask you, which spring is the stiffest? Is there any word like stiffest? Doesn't matter. Okay, which spring is the stiffest, highest stiffness? Okay, then you look at the one with the highest gradient. Which one has the highest gradient? Of course, this one, the top one, the most steeper, the steepest one. Okay, so in fact, if you draw a horizontal line like this, to extend all these springs at a certain extension, x equals to 10 cm, I just put a random value. Then you look at what is the force here, 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 and here. Of course, this one is the highest one. Okay, and then this one is the lowest one. Now, okay, so next one, next one. Now, any question, let me know, so that I can stop and you can try to just to make clear of everything. Okay, now just now we learned about the elastic region of the spring, right? Now, let's go back to the example just now at first. Okay, the spring without attaching any load. This is the original length, right? Now, let's say if I continue from the just now, I keep adding the load. You keep adding until a point. Let's say now it's already 50 Newton. Okay, it's very large. Okay, until a point where we call it, this is the extension limit. Okay, we label it as X limit, extension limit, because impossible you can keep on extending the spring forever, right? Okay, and eventually until one point, the spring will break. Okay, the spring will break, but before it breaks, it will reach one point where the spring no longer has the ability to return to its original length. Okay, so I repeat my sentence here. It will reach, if you keep on extending, it will reach one point. Okay, it will reach one point where the spring no longer has the ability to return to its original length, and this point is we call the elastic limit. Okay, the elastic limit, elastic limit. Okay, so meaning that if you keep on extending the weight, increasing the weight here, and the spring extend beyond its elastic limit, what happened when you release this load? If you remove the load, you will see that this one is the spring without load, without the load. So you will see that it is still extended. This is the original length, and this is the extension. And this extension, this extension here, it becomes a permanent extension. Okay, simply because you have extended beyond its elastic limit. So this process here, we call it the inelastic or plastic region. Okay, so we can say that the object now has undergone the plastic deformation. Okay, remember just now the deformation, right? So this is plastic, or we call it the inelastic deformation. Now, from here, if I continue to plot my graph, so let's say this is my graph again, F, N, X, and Cn. Just now it's straight line, right? Straight line until a point where this is the elastic limit. Okay, so this is elastic limit. So beyond the elastic limit, the curve will no longer move in straight line. It will become like this, something like a curve. Okay, so it will become like this, and we can say that the force is no longer directly proportional to the extension, okay, beyond the elastic limit. So if you label it here, so the first one, you have the elastic region, and this is the inelastic region. Okay, so what happened in the inelastic region? Why this happened is because when you extend it beyond its elastic limit, right, what happened is that the molecules inside the spring, the internal molecules, which will start to wear, it will start to tear apart. Okay, so when you let go of the force, it no longer returns to the original length because of the already deformed. So we say that in this region here, in elastic region here, we say that the extension is irregular. Okay, extension is irregular, meaning that irregular means that it does not follow any rules. Just like the equation F equals to kx, right? This is the straight line rule, right? So we can easily predict the extension based on how much force we apply if the spring is in its elastic region, because it follows this rule, it follows this equation here, right? It is directly proportional. So in the plastic region, where the extension is irregular, it does not follow any rules. Okay, it can go wherever it likes. So it is not predictable. Okay, so other words, meaning that in this region, the extension is not predictable. Not predictable. Okay, so if you keep on increasing the force, so until one point where the spring will fail, it will break, right? It will break. So this is we call the breaking point. Okay, so if I continue to plot this graph here, eventually this last dotted line here, I put another color. Let's take it a green color. This green dot here, we call it the breaking point. Okay, so beyond this point, the spring breaks and everything fails. Right, so this graph here, it shows the extension behavior of a particular spring. Okay, so at first, okay, let me repeat this one. Okay, I erase this one first. Just a recap on this one. So at first, you have graph F Newton and X Cn. So at first, directly proportional, so it is straight line. So here we can use the equation f equals to kx, where k is the gradient of the graph. Okay, equals to m. Now, directly proportional, if you keep on extending, so this region here is very easy to predict. It's very easy to calculate the extension based on how much force you apply. Okay, if I apply 2n of force, provided if the spring constant is given, then I can calculate the extension using the formula f equals to kx, right? So if I keep on extending until one point is, we call it what? We call it the elastic limit, right? Elastic limit. So beyond this elastic limit is where the plastic region occurs. And it is like curved like this, okay? Curved down a bit, like a dome shape, okay? And after that, eventually it will reach this final one, which is the breaking point. Okay, so this graph is not exactly curved like so beautiful, curved like this. No, it's sometimes it like curvy a bit. Okay. Now, this one shows the behavior of the extension of the spring. Now later I will teach you how to we apply the Hooke's law. How do we apply the Hooke's law to calculate the extension of the spring? Okay, so at the back is at the later part is mostly about the calculation part. Okay, now I have 1 minute left here. Let's log out and log back in. I'll send the link again. You guys join again and we'll continue from there. Okay.